Okay, so no pictures for this one, just words. We'll have to make our own picture. A sodium ion, Na+, and a chlorine ion, Cl-, are suspended in a saltwater liquid 5.0 nm nanometers apart. What is the magnitude of the electric force from Cl- on the Na+? Is the force attractive or repulsive? I am relying on a little bit of chemistry knowledge for this one, but that's okay since I'm doing the problem for you. Hopefully that's fine. And a little bit about terminology here. We'll sort of remind ourselves what is a nanometer, what's a coulomb, etc. Now, we're being asked about the magnitude of the electric force and whether it's attractive or repulsive. I think one of those questions you can already answer. But let's first sort of remind ourselves, what is the electric force? And there's two equations to think of here. We have to decide which one we're going to use, okay? The first one is this one, it's Coulomb's law. So F equals Ke Q1 Q2 over R squared with a bunch of brackets on the side indicating absolute value. Don't be scared by the brackets or the arrow on the F. So the arrow on the F is just reminding us that F force is a vector and it has a directionality. And so positives and negatives are important if you wanted to talk about forces. On the other hand, the absolute value signs are telling us that this equation, this Coulomb's law, this version of it anyways, doesn't tell us about direction. And so we have to ignore every positive and negative that comes out of this problem. This is only about the magnitude, okay? But this is a big one. This is a big equation, and it should pop into your head anytime you're asked about the electric force, okay? You might not always use it, but especially when there's a force between 2 point charges, two sort of points in space, okay? Then Coulomb's law is very useful. The other version is F equals QE, and this is saying that if there's a charge of value Q, charge Coulomb's Q, in some electric field E, it's going to feel a force, F equals QE. Notice that there aren't any absolute values this time. That's because if the electric field is positive, meaning it's say pointing to the right, and the charge is positive, then the force is to the right. But if the electric field is positive and the charge is negative, positive times negative is negative, the force will be to the left. Okay, so directions are determined in this version of the equation. But let's think about which one applies to our scenario here. I don't see anything about the electric field. I don't see anything about voltages or electric potential that could lead us to an electric field, so we're probably not using the second version. We're going to use Coulomb's law, and let's write it down. F equals Ke Q1 Q2 over R squared. Yeah, these are absolute value, but again, that doesn't mean much. It just means ignore my negative signs, okay? This is going to be the magnitude of the force between 2 point charges, like if you had, say, a positive charge and a negative charge, which is actually what we have, right? We have a positive sodium atom and a negative chlorine atom or ion. A reminder, right, that an ion is an atom which has an unbalanced number of protons and electrons. And so this is the chemistry knowledge coming in. If it's sodium plus, what information does that give you? And you kind of already know you're using this equation. Ke is a constant. R is the distance between them, which that looks like this 5 nanometers here. But it's these Q values, the coulombs, that were not given. And so that's information is hidden in the chemistry here. A positive chlorine ion means that it has one more proton than electron, okay? So that means that it has, its charge is equal to, so its Q of the sodium is equal to, let's see, the positive version of the electron charge. Conversely, a chlorine ion has one too many electrons, and so, well, it's equal to, let's make it very explicit, the negative version of the electric charge here. Okay, so meaning here, no matter what it is, this is a negative value. This is a negative number. This is a positive number, and they're the same number. That number is well, E is equal to 1.6 times 10 to the minus 19 coulombs. I had to double check there. And so for an electron, that's a negative number. For the extra proton, that's a positive number. Okay. And now we have just about everything. Now we just need to double check. Okay, so 5 nanometers. My R is equal to 5 nanometers. And let's do the easy thing, which is don't mess with squaring a nanometer and trying to figure out the units. Let's first convert this to SI. A nanometer, nano 9, is 10 to the negative 9 meters. Nano, it's a billion. Nano 9, that's how I remember it. Okay, and so that's the number that we're going to square, okay? That's the distance between these sodium and chlorine ion. Ke is a constant, and let's see what it is here. That's 8.99 times 10 to the 9. We'll just go ahead and round. We're not really being too precise here. 9.0 times 10 to the 9. 9 times 10 to the 9. And the units are kind of funny. Newtons meter squared per Coulomb squared. And let's try and keep those units attached. It'll help us by the time we get to the end of the problem. We're really ready to start plugging everything in. The force is equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. We can ignore the absolute values. That's just saying whatever we get is going to be positive. So that's 1.6 times 10 to the minus 19 times, and again, so I could put in a negative 1.6, but it doesn't matter if we're taking the absolute value. 10 to the 19 coulombs divided by, and then this is 5 times 10 to the minus 9 meters, all squared. Okay, and now you can get your calculator out if you want. I'm going to do this a little bit carefully here. So let's first look at the units, right? You see there's 2 coulombs up here, which will cancel out this Coulomb squared. This meter is going to get squared, and that will cancel out this meter squared. And so we should be left with just newtons, which makes sense for a force. Okay, so that's how units can help you. If you keep them attached, don't be lazy. Units are your friends, okay? Now let's go ahead and type into our calculator. If you're the kind of person that has issues with calculators, I would say do all of these numbers first and then get to the magnitudes. Common problem, trust me. Okay, so I'll type it into my calculator. I got that the force is equal to 9.216 times 10 to the minus 12. And as we said, newtons are all that's left over. And that's it. That's this problem. It's just a Coulomb's law type problem. You have to identify the correct formula. That's the main sort of thing here. This whole second part about the electrons is more for fun. I probably on an exam would give you a little bit more information than that. You know, it has an extra electron. Then you have to decide that the charge is that. Yeah, so hopefully that made sense. This is a sort of bread and butter type problem where you really want to make sure that it's not confusing at all because it leads to other problems. So make sure that if you have any questions, you open up your notebook right now and write down a question so that we can discuss it. Okay, thank you, folks.